Bismillahirrahmanirrahim. Today we will be discussing deadlock in operating system. This is one of the common issues that are observed in our systems. What all we will be discussing in this chapter? Let's see the discussion agenda. The discussion agenda for this chapter is in front of you. First, we will try to understand with some examples what actually deadlock is. Then diagrammatically, I will try to show how deadlock can be represented in order to enhance your understanding with the topic. Then we will be discussing what are the basic characteristics of deadlock. Then we will be talking on different methods to handle deadlock. That includes deadlock prevention, deadlock avoidance, and deadlock detection. At the end, we will be talking on mechanism, how we can get our system back if it ever is stuck in deadlock. Coming to the first point, deadlock problem. Let's see what is deadlock and how it is considered as a problem. What is a deadlock? The definition of deadlock is in front of you. The definition says, set of blocked processes, each holding a resource and waiting to acquire a resource held by another process in the set. What does this definition mean? Let's develop our understanding with the help of an example. For example, we have two tape drives in our system and there are two processes, process 1 and process 2. Both of them are holding one tape drive each, but require another one to complete their respective task. Block state, as mentioned in the definition, is the state, or it is also known as waiting state, when a process is waiting for some resource to be assigned to it, or it is waiting on the resource or getting executed on the resource. We have discussed block state in chapter 2. So now the situation is two instances of tape drives are there and both of them are being held by two processes each. But they are not proceeding ahead as they require one more instance of the tape drive. So what are they doing? Neither they are moving ahead themselves, nor they want each other to move ahead. So this situation is known as a deadlock. Deadlock is a very common problem which we may face in our daily routine. Here a road and bridge is shown to make you understand more about the deadlock. Traffic is shown in the diagram. The cars represent processes and the road as well as the bridge in between two roads represent the resources. These resources are being used by the cars to reach to their respective destinations. Now, as you can see, the roads are two-way, but the bridge in center is one-way. Traffic on both sides of the road have already acquired their side of road, but want the bridge to be given to them as well. Now, since only one side of traffic can cross the bridge at a time, so both sides of traffic confront each other when they reach the bridge. Here, the traffic goes jam. Unless and until one side of traffic backtracks, the jam cannot be finished. So this situation is known as a deadlock, as no one gets its work completed using all the required resources. Now, if one side of the traffic is backed up, the starvation may be the result for the traffic on that side. How? It may be possible that only one side of the traffic is always backed up. When there is a deadlock, so the cars on that side may not get enough time to use the bridge. Similarly, if one process in your system is always deprived of resources, it may face starvation. System model is the next topic of discussion. We would see how in system we can represent a deadlock. How deadlock can be represented in our system. Diagrammatically, I will try to create a system model showing deadlock. The resources in our system can be represented with alphabet R. Resource, as you all know, can be hardware such as CPU, cycle, memory, I/O, etc. One resource may have different instances, such as we have different types of memory in our system, like primary memory, secondary memory, and different hardware represent them. Like primary memory, we have RAM and ROM, and for secondary memory, we have different types of removable storages and disk as well. So the instances of a resource R can be represented by alphabet W. Processes can be represented with alphabet P. How a process utilizes a resource. The sequence is given there. A process first has to request the required resource. If the resource is available, it will be assigned to it. The process will have to utilize it, and after using, the resource will be released by the process so that other processes can then use it. Next point of discussion in the outline is deadlock characterization. What are the characteristics that signify a deadlock? There are some characteristics or conditions or requirements for a deadlock to happen in our system. These conditions are mutual exclusion, hold and wait, no preemption, and circular wait. Let's discuss all of them one by one. First condition is mutual exclusion. Mutual exclusion has already been discussed in detail in previous chapter. Mutual exclusion means one process at a time will use the resource. Second condition is hold and wait. This simply means that a process may be holding a resource and waiting for another resource to be assigned to it, and that resource may not be available at that time. So this is the exact explanation of deadlock. The process will not proceed its execution with one resource. Instead, it will be waiting for the other required resources. Third condition is no preemption. Preemption, as you all know, is to take away a resource from a process without its consent. We have seen this in chapter 3 when we were discussing different CPU scheduling algorithms. Some of them were preemptive and some were non-preemptive. So here, no preemption means a resource cannot be taken away from a process forcefully. The process can only voluntarily release the resource after its use. Fourth condition is circular wait. Processes are waiting for each other in a circle. They actually are not waiting for each other. Rather, they are waiting for the resource held by other processes. Such as in diagram, process P0 is waiting for a resource held by process P1. And process P1 is waiting for a resource held by process P0. So they are forming a circle. Similarly, big circles can be made when more processes will be involved in circular wait. Such as process P0 will be waiting for a resource held by P1. P1 will be waiting for a resource held by P2. P2 will be waiting for a resource held by P3, and so on until the last process in the circle, such as Pn, will be waiting for the resource held by P0. So they will form a big circle. It is important to mention here that in order for a deadlock to occur, it is important that all these four conditions must occur simultaneously. If one of the conditions does not occur and other three are present, still deadlock will not happen. Now we are going to create resource allocation graph. Resource allocation graph will represent the pattern how resources are allocated to different processes. As we have already mentioned earlier, resources are represented with alphabet R and processes with alphabet P. So now we need to connect resources and processes using some edges. Two types of edges are mentioned here: request edge and assignment edge. There is one more type of edge which we will discuss later on. The request edge will be drawn from a process towards the resource. that will show that a process is requesting this resource. And if the requested resource is assigned to the process, so the edge will point from resource towards the process. Both the edges must be directed so that you can differentiate which one is request edge and which one is assignment edge. We can now draw all the resource allocation graph in which processes are represented with circles, resources are drawn with squares, or you can also draw it with rectangles, and if more than one instances of a resource are there, so we can draw same number of small squares or small circles inside the big square. As you can see, we have a big square, and inside the big square we have 4 small squares. You can also draw 4 small circles showing this resource has 4 instances. So if there would be 2 instances of a resource, you would draw 2 small squares inside the big square or 2 small circles inside the big square. Request edge will be drawn from circle, which represents a process, towards the square, which represents a resource. And the assignment edge will be drawn from square towards the circle. If more than one instances of a resource are there, such as the one shown in the figure, so the request edge will end at the border of the big square. That will show that this process is requesting one instance of this resource. And when the assignment edge will be drawn, that must be drawn from internal small square towards the circle. If you have drawn it from the border of big square towards the circle, that would mean you have assigned all the 4 instances of the resource to a single process. So be careful while drawing resource allocation graph. This is a diagram showing resource allocation graph. As you can see, there are 3 processes, process 1, process 2, process 3 represented by 3 circles. And 4 resources are there, resource 1, resource 2, resource 3 and resource 4. Some of the resources have more than one instances, which are shown by small circles or small squares inside the big square. As you can see, resource 2 has 2 instances and resource 4 has 3 instances respectively. Diagram shows process P1 is requesting resource R1. So a requesting edge is drawn from P1 towards R1. But resource R1 is assigned to process P2, and you can see the assignment edge from R1 to P2. P2 is holding resource R1 and requesting for resource R3. But R3 is assigned to process P3. Resource R2 has 2 instances. As you can see, they are assigned to process 1 and process 2 each. Resource R4 has 3 instances and is not requested by any process. So it's all 3 instances are available. So this is how we draw resource allocation graph. This is resource allocation graph showing deadlock. Can anyone highlight the deadlock? The best way to highlight deadlock is to monitor the circular weights. Now check how many circles can be drawn among processes. We can see two circles here. How? One circle is P1 is waiting for P2 and P2 is waiting for P3. P3 is then waiting again for P1. Let me draw it. So here you can see one circle. Another circle can also be drawn. P1 waiting for P2 and P2 waiting for P3, and then P3 is waiting for P2. Let me now draw it again. So you can see two circles here. All of the three processes are in deadlock, as all of them are holding some resources and waiting in circle for another resource held by other processes. Mutual exclusion is also applied, as one resource can be assigned to a single process at a time, and no resource can be forcefully removed from a process. Since all the four conditions of deadlock can be observed in this diagram, so this represents a deadlock. We need to now apply some mechanism to eliminate deadlock, which we will be discussing later on. This is another graph which has a circle, but still it is not considered as deadlock. Why so? Because we have a deadlock breaker in this diagram, which is process P2 and another process also, process P4. Both are working as deadlock breakers. As you can see, a circle between P1, P3 on resources R1, R2. Let me draw it. Both the resources have two instances. One instance of resource R1 is with process P2 and other instance is with process P3. Similarly, one instance of resource R2 is with process P1 and other instance is with process P4. Since P2 and P4 have no further request, so they can break the circle between P1 and P3. After utilizing, P2 will release resource R1, which will be assigned to process P1, and the circle will break. Similarly, P4 will utilize resource R2 and release, which will then be assigned to process P3, and the circle will break. So whenever there are circle breakers in the resource allocation graph, such situation is known as Livelock. Livelock is flexible and temporary as compared to deadlock, as deadlocks are hard to break and generally long-lasting. That is all for now. We will continue it in next lecture. I thank you all.